Find the area of the region enclosed by one petal of r equals 8 sine of 2 theta. So now this is where the understanding of how these polar equations actually map, because we have to get one petal here. So there's a start and a stop to that. And it doesn't give us the bounds for that, but we have to find the bounds. So what we're going to do is we're just going to do a simple graph here of this r equals 8 sine of 2 theta. And that's going to help us to set up the integral to actually find the area of this enclosed region. So here's our r theta table. So I'm just going to start filling it in. So again, I'm going to go by pi 12ths for this one because I see 2 theta there. So we're going to do 0, pi 12ths, pi 6ths, pi 4ths, pi 3rds, 5 pi 12ths, pi halves, 7 pi 12ths, and 2 pi 3rds. I'm not going to have to go all of these probably. All I need is one petal here. So now I'm just going to plug in all my, find my r's for these thetas here. So when I plug in 0 for theta, it's really going to be 8 sine of 0, and sine of 0 is 0. So then I'm just going to fill in the rest of these values. So one thing you notice, I don't know if you noticed this or not, but I made it back to 0 again. So I started at 0, which was great, and then I ended at 0, which means that's going to give me one petal. Now take a look at this as we continue. So there's 0, 0. There's pi 12ths, 4. And there's pi 6th, 6.928. And then I'm going to go to 45 degrees now, which is pi 4ths, and that's going to be 8. And then I'm going to go to 60 degrees, which is going to be 6.928 again. And then I'm going to go to 5 pi 12ths, and that's going to be 4. And then back to 0 again. So I'm back here now. So there's actually one petal, so that's why I stopped. And one of my big indicators here was I started at 0 and ended at 0. So that tells me I'm going to get exactly one petal there. So if you take a look at this mapping now, that's exactly what we see here. So that's one petal. So I'm going to run from, now if you think about this on the larger scale, I'm going to run from 0 to pi halves. And those are going to be my bounds for this. Now keep in mind when I'm doing these areas here, remember I'm talking about sectors here. So if you think about this idea then is I'm just going to start taking these, creating these sectors in a sense. And that's really what I'm looking at here. And then I'm going to squeeze those down so that this point is sitting on top of this point. So actually I get a ton of lines in there. And those lines are going to fill the entire space. And that's really the idea of what we're doing. And we're running from 0 here all the way to pi halves. And that's what we needed to create this one petal. So that's what I want you to see. So we do really have to understand that mapping here. And that's the big thing. Realize I'm going in this direction here. So I'm starting there, I'm going around, and I'm coming back around again, and that's going to fill my space. And that's essentially what I'm doing with my integral here. So now to set this integral up, it's going to be the integral from 0 to pi over 2. And my formula says 1/2. And remember it said f theta squared d theta. But our f theta here is actually 8 sine of 2 theta. So that's what we're going to put there. Actually, I could keep all that so you can remember where everything came from. So then when I set up my integral, it's going to run from 0 to pi over 2 times 1/2, and it's going to be 8 sine of 2 theta squared d theta. So that's the integral we're looking at here. And when I square all this in here, I'm going to pull that 1/2 out. No, actually I'm not, because I'm going to be able to get rid of it, because I'm going to be able to times it here. And this is going to be 1/2. And then in here I'm going to get 64. And sine squared 2 theta. D theta. Now I can see here that I'm going to take 1/2 times 64. And that's going to be the integral from 0 to pi over 2 of 32 sine squared 2 theta d theta. So then from here we get 0 to pi over 2 of 32 sine squared 2 theta d theta. And that's as far as I want to go with this one. We can definitely plug it in our calculators and get an answer for it. But to actually work this one out, it will take a few identities here in a somewhat crafty way to take care of this squared component here and this 2 theta component. So looking at a bunch of identities that way, it would take a couple of them and some algebra there to actually get somewhere with this problem to integrate it. So anyways, our final answer for this one turns out to be 8 pi once we plug it in with our bounds on our calculator. Okay, so there's our answer for this one. It's 8 pi. So you kind of see then how it's important to understand how these map so that we can understand lower bounds and upper bounds and about how it's actually going to travel. So just something to think about as we go through these. All right, so let's try another.